Hello students, so in this class we will extend the discussion on partial derivatives and we'll study Euler's theorem and its applications. Before moving forward, let us try to understand what homogeneous functions are. A homogeneous function fxy is said to be homogeneous of degree n in the variables x and y if it can be expressed in the form x raised to power n g y upon x or in the form y raised to power n g x upon y. Okay, in homogeneous functions each term is of same degree. Okay, um, there are certain remarks. So one is a function fxy is homogeneous function of degree n if f dx comma ty equal to t raised to power n fx comma y for all values of t where t is independent of x and y. Okay, second is a function fxyz is said to be homogeneous of degree n in the variables x, y and z if it can be put in the form x raised to power n f of y upon x comma z upon x, or if f dx dy tz can be written as equal to t raised to power n f x y z for all t. Another point is, if u is a homogeneous function of degree n in x, y and z, then each of the partial derivatives, first order partial derivatives ux, uy and uz is a homogeneous function of degree n minus 1. So now coming to example 1. Okay, so if fxy is equal to x square plus 2hxy plus y square, then fxy is equal to, it can be written as taking x square common, so ax square upon x, or simply multiplying and divided by x square, so ax square upon x square plus 2hxy upon x square and y square upon x square. And if we divide by x square, I get x square a into y upon x is so 0 to h y upon x and y upon x square. So yes, this matter in the bracket is just like a function of y upon x. So let's say gy upon x. So fxy can be written as x raised to power n gy upon x, where n is equal to 2. So this is a homogeneous function of degree 2. Okay, similarly you can check y upon x, x and inverse y upon x and x square log y upon x. These are the homogeneous functions of degree 0, 1 and 2 respectively. You can apply the same method. Okay, coming next, example 2, and if f is equal to this, x raised to power 1 by 2, y raised to power 1 by 2 and z raised to power, x raised to power 3 by 2 plus y raised to power 3 by 2 plus z raised to power 3 by 2, then taking x raised to power 3 by 2 common, I get this one. And you can see this is just like zy upon x, okay, and z upon x also. Okay, and hence this is a homogeneous function of degree 3 by 2, right? Euler's theorem on homogeneous functions. Coming to Euler's theorem on homogeneous functions. So what is the statement? If fxy is a homogeneous function of degree n in x and y, then x into del del x of f plus y into del del y of f is equal to n times the function f. This is the statement of Euler's theorem and its proof. Now since f is a homogeneous function of degree n in x and y, then f is equal to x raised to power n gy upon x. It's by definition. And now we have to find out partial derivative with respect to x and y. So del del x of f, This is first function and the second function. First function derivative of second function, and then similarly second function derivative of first function. So if we expand it, I get this one, okay, and x times delta x of f is this one, x raised to power n minus 2 multiplied by x, so plus 1, okay, x minus 2 plus 1, that is x raised to power n minus 1, and y gy. And similarly here also plus 1 because multiplying yx, so it is n into x raised to power n gy upon x. Again, del y of f is simply because x raised to power n independent of y, so only differentiation of this is required. Okay, so g dash y upon x into derivative of y upon x with respect to x, that is 1 upon x, and we get x raised to power n minus 1 g dash y upon x. Then y into del y of f is this one, okay, to adding 1 and 2 we get x raised to power n minus 1 y g dash y upon x plus n x raised to power n g y upon x plus what we got, x raised to power n minus 1 y g dash y upon x. This with this cancels and you're left only with this one, but this part x raised to power n g y upon x is simply your f. So therefore it is n times f, and hence this is the proof of Euler's theorem. X into fx plus y into fy is equal to n times f, where fx and fy are nothing but del x of f and del y of f respectively, first order partial derivatives of f with respect to x and y. Yes, coming to question based on Euler's theorem, show that the following functions are homogeneous and verify Euler's theorem. So these are the two functions. Z is equal to this, okay, taking y square common, okay, we are getting this, and then this can be written as x upon y, f of x upon y. So this is z is equal to y square z x upon y, so therefore it is a homogeneous function of degree 2 in x and y. This is by definition, okay. And yes, verification, Euler's theorem verification you are doing, then first of all directly we are finding del x of z and del y of z. So del x of z is just like this, y is independent of x, so only the derivative of x into f upon y is required. So zx is equal to y outside x into derivative of this with respect to x, and then this into derivative of x with respect to x. So if I do this differentiation, I get this, and if I multiply by x, I get this one, okay. Similarly, del y of z, okay, so x will be outside and y into fxy, derivative of y into f of x upon y with respect to y. So if I do this, I get this, and further expand, I get this, and this will be equal to minus x square upon y. This is y, minus x square upon y, f dash x upon y plus x of f x upon y. Then y into zy is simply multiplying by y, I get this one, and hence x into zx plus y into zy is this one. This is x into zx and this is y into zy. So these two terms cancel out, you are left with this. This is 2 times xy. So this is z, and therefore this is 2 times z. Also z is a homogeneous function of degree 2 in x and y. Therefore x into zx plus y into zy is equal to 2 times z. And hence from 1 and 2 Euler's theorem is verified. Okay. The next is second part. So here it is already in the forms y upon x, y upon x raised to power n. So it is a homogeneous function of degree n. Therefore, by Euler's theorem, x into zx plus y into zy equal to n times z. Now we have to verify it. Okay. So directly we will find zx. So z is nothing but the derivative of this with respect to x. So okay, the derivative of x raised to power n into the second function as it is, and then similarly this one. So if we do this calculation, we get x raised to power n minus 1 plus n x raised to power n minus 1 log of y upon x. Okay, call it equation 1. Similarly, find zy. So this is nothing but x raised to power n independent of y. So derivative of log of y upon x only with respect to y. So this is the derivative. Okay, and x raised to power n x upon y into 1 upon x square. 1 upon x. Okay, x with x cancels. You're left with x raised to power n. Y going up, y raised to minus 1. So therefore x into zx plus y into zy is, if we add this, we get this, and this is nothing but your z. So it is n times z. Hence from 1 and 2 Euler's theorem is verified. Thank you.